IP Tech Talk. Hello everyone, welcome to IP Tech Talk. In this video, I will introduce how Huawei Intelligent and Lossless Data Center Network implements lossless transmission of packets on the Ethernet network. Huawei Cloud Engine series data center switches build intelligent and lossless networks from two aspects: network optimization and integrated optimization of networks and applications. Today, I'm going to talk about flow control technology used in network optimization. As introduced in the previous video, packet loss prolongs retransmission delay and degrades applications. In fact, there is another important reason for avoiding packet loss on data center networks. RDMA technology has been widely used for improving application performance on high-performance application servers, such as distributed storage, cloud HPC, and AI training servers. However, RDMA-capable servers are sensitive to packet loss, so data center networks connected to RDMA-capable servers must be lossless. So, what is RDMA? RDMA is short for Remote Direct Memory Access. It allows direct data read and write operations between applications and NICs, improving on traditional TCP/IP technology. RDMA reduces the protocol stack delay to as low as about 1 microsecond. In addition, RDMA allows the receiver to directly read data from the memory of the transmitter, which greatly reduces the CPU load. For these reasons, RDMA is very popular in high-performance applications. However, RDMA was initially carried on a lossless InfiniBand network and lacks a comprehensive packet loss prevention mechanism. RDMA packets can be transmitted at full speed on a lossless network. But once packet loss occurs on the network, the end-to-end RDMA performance deteriorates sharply. Just a 1% packet loss rate will cause the RDMA throughput to drop to 0. To prevent the RDMA throughput from being affected, the packet loss rate must be less than 1 in 100,000, or even as low as 0. To reduce the dependency on dedicated networks and enable RDMA to be carried on Ethernet network, the Ethernet network must be lossless. However, congestion-triggered packet loss is a typical characteristic of the Ethernet network. So how can we ensure zero packet loss on the Ethernet network? The answer is using flow control. Flow control technology is the IEEE 802.3 defined Ethernet pause mechanism and works like this. When device B cannot receive excess traffic from device A, it proactively sends pause frames to device A and requires device A to suspend traffic transmission and to only continue sending traffic after a period of time. Although flow control based on the Ethernet pause mechanism can prevent packet loss, there is a downside. That is, all traffic on a link is interrupted for a period of time. This is unacceptable for applications, and this is where PFC comes in to the rescue. PFC divides a device interface into 8 virtual queues with priorities ranging from 0 to 7. Each queue has its own buffer space for packets. When congestion occurs in a queue on the interface of device B, the device sends a PFC frame to device A, which can be considered as a stop signal. After receiving the PFC frame, device A stops sending packets in the corresponding queue and buffers packets on the local interface. If congestion also occurs on device A, it sends PFC frames to its upstream device, and this can continue all the way to the transmit server. In this way, packet loss due to congestion is eliminated. With PFC, instead of interrupting traffic on the entire interface, only traffic of certain queues is suspended. In addition, queues do not affect each other, which allows multiple types of traffic to be simultaneously transmitted over a link. On the Intelligent and Lossless Network, PFC-enabled priority queues are called lossless queues and are used to carry packet loss-sensitive service flows. In contrast, PFC-disabled queues are called lossy queues and can be used to carry service flows that are tolerant to packet loss. However, there is a potential risk with PFC. In some scenarios, for example, the server NIC keeps sending PFC frames due to a server NIC fault, causing PFC frames to spread further throughout the network and even leading to a PFC deadlock. A PFC deadlock occurs when multiple devices send PFC frames to each other and wait for each other to release resources after congestion is relieved. This causes traffic to be permanently blocked. Once a PFC deadlock occurs and is not removed in a timely manner, lossless services will be interrupted, or in some cases, the entire network will break down. To solve the PFC deadlock, Huawei Intelligent and Lossless Network provides two technologies: PFC deadlock prevention and PFC deadlock detection. First, let's see what PFC deadlock prevention is. In the typical spine leaf networking of data center networks, if a leaf node detects that a service flow comes in and out through interfaces connected to spine nodes, the service flow is considered a high-risk, hook-shaped flow that may cause a PFC deadlock. In this case, Huawei switches will switch the service flow to another queue to change the PFC path to prevent loops caused by PFC frames, thereby avoiding a PFC deadlock. So, what is PFC deadlock detection? Well, PFC deadlock detection is used to detect PFC frames on device interfaces. If a device continuously receives PFC frames throughout a certain period, the device considers that a PFC deadlock may occur and does not respond to the PFC frames for a period of time. If a large number of PFC frames are detected in several consecutive periods, the device considers that a PFC deadlock has occurred. In this case, PFC will be disabled to protect corresponding services. Well, that's all for today's IP Tech Talk. Next time, we'll be talking about how Huawei Intelligent and Lossless Network implements high throughput and low latency. Thank you for watching.